good error yesterday. I mean, that's one of the problems of
the G's and the A's, yeah.
That's right.
I just turned this on. Can I give it to you? And we're at time, so as soon as you're ready, we can get started.
I'll just put a few more words on the board and then I can start. All right, welcome back, everyone. The third lecture on quantum computing for quantum field theories. So today we're gonna actually primarily talk about quantum computing now after 2 lectures. So we're gonna see how we can then turn the gauge theory, at least the one that we described, the abelian gauge theory of the Schwinger model, into the language of quantum computers and then simulate its real-time dynamics. So before doing that, I have to give you a few basics of quantum computing and quantum simulation strategies. It is good that I'm giving this talk to a group of quantum field theorists, so you know already quantum mechanics. I don't have to spend a lot of time on some of these basics, but I'll tell you what you need to know. So we'll talk about qubits, gauge circuit. I will tell you how to encode fermions and bosons into the qubit, so that we can turn our Hamiltonian into a qubit Hamiltonian, okay? And then we talk about at least one common strategy of simulating time dynamic, which is based on trotterization or product formulas. But I want to spend some time to tell you that there are errors associated with these, and we have to quantify those errors, or at least keep track of them in the simulation. And I will tell you about a few simulation strategies qualitatively, what are the different steps involved to be able to simulate any qubit Hamiltonian in terms of these product formula algorithms, okay? Then once we have this background, we're going to start to think about the model that we've been studying, Schwinger model, and then see how we can actually simulate its time dynamics in both of the forms that I gave you yesterday, which is both purely fermionic formulation, because we could remove all those bosonic degrees of freedom, but also I want to show you how you can actually simulate the full form, because eventually you have to deal with these bosonic gauge degrees of freedom. So what would be the tricks that you can implement to also encode those kind of Hamiltonians? I will tell you kind of a little bit about the things that we didn't cover, so that you can go and hopefully study more. And I'll have some references in the notes. And then maybe in the last 10 minutes, and I ask Ethan to tell me when I am left with 10 minutes, so that I can actually show you some cool examples over the slides of the kind of things that people have done that are of relevance to nuclear and hydrogen physics so far. So the actual sort of developments in terms of implementation, algorithms, and so on, okay? So that's the plan. I can just move this up here. So let's talk about the basics. Qubits, gates, circuits. Okay, let me ask you, how many of you have seen a course in quantum computing? Okay, that's a good fraction, about half. All right, so let's just start very simple. I mean, it's just quantum mechanics. A qubit is a 2-dimensional Hilbert space. It could be a spin up or down, depending on what hardware technology that you have. You may encode this 2-dimensional Hilbert space in whatever degrees of freedom you've got, okay? But in any case, at the formal level, a 1 qubit state is simply just A, some amplitude, times 0, plus B, some amplitude times 1. Or in the vector form, I can write it as A 1, 0, plus B 0, 1. It's a bit counterintuitive that in quantum information science, the lowest energy is kind of the up-down as opposed to down-up. So this is called computational basis, and you get used to it. So 0 is the one that comes with 1, 0, and then 1 is the one that comes with 0, 1, just by convention. OK, so if you have now a sigma z operation that is acting on this guy, is going to give you a positive eigenvalue. If you have a sigma z that acts on this guy, it's going to give you a negative eigenvalue. That's the convention. OK, what about 2-qubit? Well, the state of 2-qubit is just simply then more amplitudes, right? And then in this convention, we have 0, 0, and then 0, 1, 1, 0, and then 1, 1. And again, in the vector form, you can write this as 1, 0, 0, plus b, 0, 1, 0, 0, and then, of course, the rest. OK? So how many parameters do we need to characterize a state that looks like this or this? Well, these are complex numbers. So in principle, I have 2 times 2, 4 parameters that I need to parameterize this. But one of them is going to be an overall normalization, right? So if you normalize your single qubit state to be just 1, then you can just write this as cosine of some angle theta over 2 times 0 plus e to the I phi sine of some angle over 2 times 1. And you may be familiar with the term block sphere parameterization. These are sort of those angles on the sphere. And then similarly here, then I'm going to have 2 times 2 times 2 times 2 parameters. If I normalize the state, one of them is just a phase, overall phase, and therefore it's going to be 2 to the 4 minus 1, and so on. And then you can write the state of multiple qubits as a direct or tensor product of the state of multiple qubits. With a convention that we start going from 0, 0 to 0, 1, and then 1, 0, 1, 1. OK, so that's the computational basis in literature. OK, so what about gate? A gate is simply any unitary operation that would act on the state of your qubit, whether it's a single qubit or multi-qubit state. OK, so u, dagger u, is equal to 1. And these unitary operations are very natural for quantum computers because that's what quantum mechanics is all about. Evolution in quantum mechanics is unitary, and therefore we can implement these unitary gates, unitary building blocks. If you ever want to implement something that is non-unitary, then you have to actually encode it in terms of a larger unitary operation on an extended Hilbert space. Otherwise, there's no way to do this sort of non-unitary operations on a quantum computer. But there are tricks to do that, as I said. OK, so what are some of these single qubit gates and multi-qubit gates? Well, the usual one is the X gate that flips the state of a single qubit. So this is essentially just sigma x acting on a qubit. And this is just 0, 1, 1, 0. Similarly, y is sigma y, 0 minus I, 0. Z is, or sigma z, is 1, 0, 0, minus 1. So these are the usual x, y, z gates. And of course, you can also implement any rotations around the x by some angle theta. And by definition, this is minus I theta over 2 sigma x over the state of that qubit. Yes?
So I have a question. If the computer only supports a finite number of operations, how would you implement an, say, Rx with an arbitrary theta? If, say,
let me get there. OK, let me just list this, and this is where I'm going. All right, good question. And the question was about how we can kind of implement something like Rx, which is a continuous sort of set of operations given angle theta using a finite set of gates. Very good question. I'll get there. And then similarly for I theta, you just replace this. And then for Rz theta, just replace the sigma x. OK? What else we can do with the single qubits? Well, we can do a Hadamard gate. which is 1 over square root of 2, 1, 1, 1, minus 1. So this is the one that would then creates a superposition of 0 and 1 for you. So that's a very useful gate. What else can we do? We can do something that is called a phase gate, P of phi, which is 1, 0, 0, e to the I phi. So it doesn't do anything on the 0 component of the qubit, but it would rotate by angle phi the 1 component. What else can we do? Well, there are specific cases of this. One of them is called the S gate, which is 1, 0, 0, and then I. So this is just the phase I sitting here. A very important one is 1, 0, 0, e to the I pi over 4. And then so on. So you can define other sort of gates, but these are like the ones that are the most important and most common, at least like for the single qubit gate. Okay? So now let's get to the difference between classical and quantum operations. As we can see here, this is a superposition, and in principle, there are infinite number of possibilities for these amplitudes because I'm talking about these continuous variables, right? So you can have sort of infinite number of gates defined on the state of these qubits that would just rotate them from one angle to the other, like on the Bloch sphere, right? And in fact, if we had access to only certain type of gates, we would have been only able to do just classical operations and not quantum. And then, for example, so if you have access to just like x, y, z, even h, and then phi, if phi is certain angles like this s, then we're just doing like discrete reflections or transitions between the states of these qubits. And it turned out that if you can write a circuit that only uses these operations, and then the ones that look like this on the 2-qubit systems, then that circuit could be efficiently simulated classically. So there is no quantum gate. And that's why this gate is pretty important, because that already you can see there's like some sort of a square root of 2 coming out of this. This is still not enough to be able to simulate something that looks like a continuous gate or continuous rotation. And that's why it is a very interesting subject to be able to synthesize gates that look like this, these continuous gates, in terms of operations that have sort of some finite number of operations in terms of these guys. Okay, so if we only had access to the rest of these guys, we would not have been able to create this. But it turned out that we have access to these T gates. We can, with given accuracy, epsilon, synthesize gates like this. And that means that we need a number of operations. And it turned out that for some of the best algorithms, you actually need logarithm of epsilon minus 1 T operations to be able to approximate something that looks like this with accuracy epsilon. Okay? So I'm not going to get into the weeds of that, but something to keep in mind. I'll mention something about this when we design our algorithms, but something to keep in mind that in order to make the circuits quantum, you need certain gates, and these gates are called non-Clifford gates. Those other guys are actually just Clifford gates, okay? All right, but this is just for a single qubit. I haven't told you about multi-qubit gates. Let's talk about now at least a 2-qubit gate. And the most famous one is what is called a controlled knot, which looks like this. What does this mean? Well, in terms of the matrix operation, it actually looks like 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. So if you notice what this matrix does, if I implement it on a state of 2 qubits, which is like this guy, then it doesn't do anything to the first, to the 0 component, but it actually switches the 1 component depending on whether this one is in 0 or 1. In other words, if I start from 0 here, I would always end up in 0 here. Or if I start in 1 here, I would always end up in here because this is by convention, this guy won't change. But if you start from 0 here, and then you have here 0 or 1, then you end up again in 0 or 1. So nothing happens to the state of this. But if you start from 1 over here, then and you start from 0 and 1 here, then you switch to 1 and 0. So this is nothing but sort of an X gate or a flip gate on this one, but it only acts if the state of this guy is 1. Okay? There are a bunch of other 2-qubit gates and 3-qubit gates and so on, which I'm not going to show you. And the reason is that you actually don't need them.
Does C9
Yes.
flip the other bit with a sigma X or sigma Y?
Sigma X. There is no phase here, right? So it's just sigma X. So why don't I need multiple qubit gates? Well, the answer is pretty remarkable because there's some theorems that show that any unitary U acting on a state of n qubits, okay, so this is going to be 2 to the n, 2 to the n unitary, can be decomposed arbitrarily closely, which means that you can efficiently, in polynomial number of operations in terms of the qubit number, get as close as possible to any unitary with a finite, sequence of a universal set of single and 2-qubit gates, which is great because otherwise, if I had a multi-qubit state over here, I would have had an exponential number of amplitudes. In principle, I should have defined an exponential number of gates to be able to kind of recover that, that operation. But it turned out that you can do it polynomially with arbitrary accuracy only with a universal set of single and 2-qubit gates. And there are options for these universal sets. One option is to use your RZ, I had Z over here, RX, RY, P phi, and then C naught. That's one option. Option number 2, which is more, yes?
It looks like P phi isn't independent from RZ. It's just RZ of like phi times a phase.
No, but for this one, this is always 1. Like the first qubit, the first component of the qubit doesn't change.
Yeah,
So that's always fixed.
You can make that stuff out of RZ by just adding an overall phase shift e to the I phi over 2 to the whole thing, which is unphysical.
But depending on whether you have a spin up or down, you get a different phase, right?
No,
Which would be different from.
The overall phase would affect both of them equally.
Okay, let's talk about this later. This is like a small point. And the set that I'm going to use anyway is this set, which is just the S, T, H, and C naught. Okay, so this is not simple. S is just that gate over there. T is the one that we really need. That's your non-Clifford gate. H and C naught are both Clifford gates. So you can already see that each of these sets should have at least one non-Clifford. This one has more, and that's why I'm picking this one, because this has just one. So if I express everything in terms of this Clifford set and this single non-Clifford, then I'm done. Yes?
What does Clifford mean, other than just like you need a non-Clifford gate?
Well, they satisfy Clifford algebra.
Okay.
This is the poly algebra. Okay. All right. So what is a circuit now? Well, it's just a bunch of yes.
What is C naught?
This one. Yeah, I should have wrote it. This one is C naught. Okay? The controlled operation. Good. So what is a circuit? It's simply just a bunch of qubits and a bunch of gates acting on them. Could be single qubit gates. It could be a 3-qubit gate that if you want to write in terms of your universal operations, you would just decompose this into this set of gates and so on. So it's just a sequence of these universal set of gates that you can use to be able to evolve a state psi to a state psi prime. That's just a circuit. And we're going to see examples of these circuits today. Yes?
I just wanted to clarify something about the theorem you wrote, which I think you didn't actually write into the theorem, but I think you said something like, if you have some universal gate set, you can always achieve a desired unitary within accuracy epsilon in
Using
polynomial complexity.
Exactly.
I think this is not true. I think generically it takes exponentially many gates, but it's just a minor thing. But
not with arbitrary accuracy, right? You can always set an accuracy where you can find an approximation with a polynomial set of gates.
yeah,
right.
But it's like the complexity generically grows exponentially with the accuracy.
Yeah, I mean, you can already see it up there, right? If I want to approximate the RZX with infinite accuracy, then I need infinite set of gates because the number of gates goes like log of 1 over epsilon, right? Okay. All right, so let's talk about the next one. Any other questions? Yes.
Yeah, so when I read this diagram, should I be thinking of that box that spans over 3 lines as operating on the
3 qubits, the top 3
Okay,
qubits.
we're operating on
All 3 of these qubits, yes. But then usually you turn it into single and 2-qubit gates, okay? Because those are sort of the primary operations that your device is set to do. Sometimes your device can do 3-qubit operations naturally, then you would take advantage of that. But in this case, usually sort of in a more standard sense, we talk about single and 2-qubit gates only. Yes?
These are the only 2 universal gates?
No, there are more sets, but these are the more common ones. Okay? Okay. So how we encode fermions and bosons in coding into qubits, which means that I have to map the Hilbert space of the fermions and bosons to the Hilbert space of a bunch of qubits that I've got, and I have to map the operations or the field operators out of the fermions and bosons to the operations on the qubits, which are those sort of operations built out of Pauli's or those universal set of gates, okay? So there are ways to do this. So let's talk about fermions first. Well, there are 2 features that are very unique about fermions, and they're related, obviously. Fermions have finite dimensional Hilbert space locally. And they also have Fermi statistics. Okay, so the first property is really good because that means that if I have a fermion sitting at the site on my lattice, I can encode it in terms of only a finite number of qubits, and I can do it exactly, right? So that's a good property. The bad property is that they have to satisfy Fermi statistics. These qubit operations, they are like bosonic statistics, okay? So they have commutation relations satisfied between them, but I need anti-commutation, which is very unnatural for those qubit operations. So how do we deal with this? Well, again, there are different ways to deal with it. The most common one is what is called a Jordan-Wigner transformation. What it does is the following. Let's say I have a psi at position x, and I want to map it into a bunch of qubits, and then a psi dagger, obviously, as position x. So one thing that you can say is that maybe I can just write this in terms of a psi minus at position x. Let's just, all of these are local, so I don't keep track of the x's anymore. So I have the psi and psi dagger. And then this one, you can maybe write at psi plus, okay? The problem is that psi and psi dagger have the following anti-commutation on every side. And then if they're at different sides, for example, psi y not equal to x, they would anti-commute. On the other hand, sigma plus sigma minus would anti-commute to sigma z, right? And this is obviously not going to satisfy the property that we want. So we can't just map this to this and this to this. You may say, why dagger to minus and psi to plus? It's just because of that computational basis that we define. It's just kind of more natural to do this. But you could do it the other way too, but you have to keep track of the fact that computational basis is kind of a different convention than what usually the physicists are used to. Yes?
Sigma plus, sigma minus also give us sigma z for the commutator as well?
Yes.
Okay.
So that's why we can't really use this at the moment. All right. So let's say that I have sites x, x plus 1, x plus 2, x minus 1, and I have a single fermion at site x, and so on. And this may actually be a two-dimensional lattice too. So then I have also another index y minus 1, xy, and so on. Then I have to first map this to a linear set of qubits. Because for all purposes, these qubits, someone would give me 1,000 qubits. And I have to kind of start and say, I want to map this to my first qubit, second, and then maybe I'll go around like this. And then maybe I come back. And then have sort of a linear index assigned with my assignment of these sites on the lattice. Okay? So then in that notation, then let's say I get to site psi of I. Okay? So the I is now the index of that qubit, all right, which is, say, sitting here. So I would identify this as linear index I. So then for that psi of x and y or z, I can just put the I over here, and then say, all right, in order to satisfy these anti-commutation relations, then I would need to have the following: sigma zj, where j is smaller than I, and then this at side I. And then let me write the other one too. J is smaller than I, sigma z j, sigma minus. Okay? So what I have done here is to introduce a bunch of sigma z's that are sitting at qubits that are before my site I, or index I. Which means that if you are in 2D, depending on how you started to index, if this is your site I, everything that is sitting before, because I started to go like this, is going to be all these sides and then these sides. So this would be the ones that are sitting before the one that I've identified. So that's why this labeling is kind of matters. Okay? And then the same over here. Then I'm not going to do that because it's a few lines of computation. But what you can show is that you get the desired anti-commutation relations by introducing this between the psi and psi dagger that are sitting at this side. But then you also recover the commutation because they have to commute anyway, even if they are fermions at different sites. But also they have to, they have to anti-commute with the 0 at different sites. And because of these chains, they actually gain that back. Okay. And this doesn't look nice, right? It's kind of ugly. And in particular, it is ugly because if my original fermionic Hamiltonian was something like psi dagger x, psi of x plus 1, and this would have been something like this over x, right? This is like a hopping of the fermions on the lattice to nearest neighbor lattice sites. If I had something like this, which is local because it's nearest neighbor, then it would turn into completely non-local qubit interactions. Why is that? Because of the sort of this indexing. If I have a guy that is sitting here, and then that would interact with the guy that is sitting here, this guy is going to have a chain of sigma z right before it, and then this guy is going to have a bunch of sigma z's. These ones would cancel, but what you're left is that you get sigma z operations on these guys between them. So this operation would turn into sigma minus at I, and then sigma plus at some I plus d, and then you have sigma z at I plus 1, all the way to sigma z I plus d minus 1. And by the way, this goes like the length of your lattice. So you turn the nearest neighbor interaction to an interaction on the qubits that could be as large as at least one length of your lattice. Okay? And that's why it's called a non-local mapping. Because what it means is that if you have an interaction like that and you want to turn it into a set of gates on your qubits, those gates could involve entanglements between multiple qubits, and those qubits would be polynomial in size of the system. Okay? It's still a very popular transformation, and the reason is that I introduced no Anshula qubit. So it's very efficient. I just need the number of qubits to be exactly the same as the number of fermionic modes, but then I get interactions that are highly non-local. Okay? What else can we do? I'm not going to tell you how they work, but I want to say that there are also local fermionic mappings or encodings. But they use a number of Anshula qubits. And this is not necessarily bad. There are some pretty compact and local encodings that use only a few Anshula qubits. So the size doesn't actually go like polynomial with the system size. These are actually pretty good. And one way to understand what's going on is that you have kind of a bunch of fermions sitting on these lattice points. And you want to impose anti-commutation relations between them. And one way to do that is to introduce a set of auxiliary fields. Sometimes you can interpret them as gauge fields. You can maybe introduce a Z2 gauge theory, which is just an auxiliary gauge theory. And then you can impose the fermionic statistics by having some sort of Gauss's laws locally on these fermions. Okay, so that's kind of the underlying idea of why auxiliary degrees of freedom would work, is that you replace the intrinsic non-locality of fermions. I mean, fermions have Fermi statistics. That means that like all the fermionic theories are intrinsically non-local. The way to turn them into local formulations is to use other degrees of freedom so that you can insert these constraints that are local, and they have to be satisfied everywhere. And because they have to be satisfied everywhere, you have that kind of non-locality still embedded, which is the thing that we talked about yesterday. We said we could have a gauge theory showing a model that has both fermions and bosons. But I showed you that you can also eliminate those bosons by using these Gauss's law, and you got a non-local fermion-fermion interactions, right? So you can trade one with the other, but you always have to have these constraints. So you can also do these formulations that are becoming very popular. The only thing is that you have to make sure that you're in particular Gauss's law sector of the theory such that you have your fermionic statistics. If you make any errors in the simulation, then you lose that Fermi statistics. Okay? So I'm not going to tell you more about this, but if you have questions about that, ask me later. So let's go to the other side and talk about bosonic encodings. Any questions? Yes.
This might be a qubit, but if you had more than 2 dimensions, wouldn't the possible number of operators not be the length, but the length to d minus 1, which is even bigger?
Yes, because if you have 3 dimensions, you have to do like another wrapping around, right? So for 2 dimensions is order L, for d dimensions is L to the d minus 1. But anyway, it's polynomial in the size of the system. Okay? All right, so what about bosons? Okay, now bosons have infinite dimensional Hilbert space locally, but they have both statistics, which is commutation algebra. And that's something that Pauli operations on the qubits would satisfy. So we don't have to worry much about this part. What we have to worry about is this part, right? So as we talked yesterday, electric field was one of those cases. It had unbounded spectrum, and we had to cut it off. With any bosonic theory, that's also the case. You always have some cutoff lambda on your bosonic excitations. Now, given that, how do you encode it into qubits? Because qubits are a bunch of 2-dimensional Hilbert spaces. So if I have n number of qubits, I have 2 to the n number of possibilities, right? So how do I then take a number, a bosonic number, let's say p, which could be a bosonic number, and let's think about just the occupation number basis for these bosons so that we can count the number of bosons that we can excite or de-excite, okay, which is a very, very popular basis. So this would be just an integer, okay? For electric field, this could be negative too. So we have to also account for when this is just an integer, not necessarily a non-negative integer. Okay, so how do we encode this? Let's define an operator, number operator that acts on the basis p and then gives back the number of bosons that is sitting in p. So again, there are choices to do this. One choice is the binary encoding, which is, again, the most common. And the reason is that it actually uses of the order of logarithm of lambda, where lambda is the number, the highest number that you can have for your bosonic excitations, number of qubits, to encode each of these bosons at each site, or at each link if you're in the lattice gauge theory, okay? So how does it work? Well, the way it works is that, well, we know how to represent an integer in binary, right? Any integer can be written as sum over j2 over j pj, something like this, where j goes from 0 to, let's call, in the notes I call this eta, so let's just call this number of qubits eta. And this goes from j equal to 0 to eta minus 1, where pj is either 0 or 1. Okay, so this is nothing but the binary representation. Let's say I have number 10, and then you have 0, 1, 0, 1, where this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and so on. Okay? So this is what it says. It says that these numbers are your PJs, and then this is your 2 to the j's, okay? All right, so here, now I can write this as, so I define Pj over here. I can now also define the state, which is going to be this P j, where j goes from 0 to eta minus 1. And this is like tensor product, okay, like this. So in terms of the qubits, you assign a qubit to this, to this, to this, and then 0 and 1 is just like up and down. It's just a binary encoding of an integer. And you encode it into these qubits. Okay? So this is nice. This has logarithm of the maximum number of excitation required to encode your bosons. But on the other hand, turned out that in terms of the operations, you would need the number of qubits squared kind of operations that you have to implement for most of these bosonic operations. That's why people have come up with other encodings too. We're not going to use them, but let me give you an example. Unary encoding. And what this does is that it would encode lambda into eta qubits, which is not really good, right? And the way it works is that you say, all right, I have 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0. And these are eta equal to lambda number of qubits. Okay? And then so you encode the first state of your bosons into this. And then if you have 2 excitations, we encode it like this and this. So you need more number of qubits. In fact, exponentially more compared to this. But on the other hand, it turned out that if, for example, you have nearest neighbor bosonic operations, because a lot of times we just excite and de-excite the bosons by 1, not more. So then that would be sort of these qubits that are sitting nearby, because this and this, you just like flip 2 of these. And then between these and these, you flip this. So it turned out that you have linear number of gates that require to do most of the usual operations on the bosonic theories. Yes?
Imagine this in each side of the lattice. Is the equation number, the bosonic equation number at each side?
Yes. It is at each site, so locally. At each site, you have this number. So if you have n lattice sites, that would be n times that number. Okay? Great. All right. So what else do we need to know before I give you an example of how to simulate the Schwinger model? What we need to know, at least one algorithm for simulating time dynamics. So let's say your unitary is e to the minus I ht. And then the question is, how do we implement this? And as I said yesterday, trotterization is a very common algorithm. It's not the only thing. In fact, it's not asymptotically the best algorithm out there, but it's the simplest. And it may also be asymptotically the best, but we don't know yet because it's very hard to calculate the error associated with decomposition. So let's talk about first order trotter or product formula. If your h can be written as a sum over hi, I from 1 to gamma, where this is not necessarily the index of your lattice sites or anything. It just could be a collection of the terms, and you call it hi, another collection of terms, and you can call it h2, another collection h3. That's that decomposition. I'll talk a bit about this in a moment. Okay, but let's say you have given this decomposition, then V1 of t, the first order approximation to that time evolution operator, is simply e to the minus I h1t minus I h2t minus I h gamma t. And obviously you have a choice of ordering these terms. I picked this choice, but any given choice can give you, in fact, different trotter errors. What is a trotter error? In this case, the spectral norm of V1 of t minus e to the minus IHT is given by And in fact, this is like an exact relation that was derived a few years back in a paper that I've mentioned in the slides, times sum over I from 1 to gamma of a spectral norm of commutation of, I need another sum, H, J, H, I, sum over J from from I plus 1 to gamma. I think that's it. So, and then this. So this is times this. Okay, so the first order Trotter formula has an error that goes like t squared. That's why it's better to have a smaller time steps for each of these so that we can reduce the error. But it also goes like all the possible commutations of the HI and HJ terms. And we had expected this, because if these operators won't commute, then this is not going to be the same as e to the I times the sum of the HIs times t. Okay, you can do other things. You can also do second order Trotter formula. What is this? This is V2 of t. And then now here, I'm going to go from e to the minus IH t over 2, e to the minus IH 2t over 2, e to the minus IH gamma t over 2 times e to the minus IH gamma t over 2, e to the minus IH2 t over 2, e to the minus IH1 t over 2. So all I did here was to do a first order expansion with t half, and then reverse the order, and then do another with t half time. And that's really cool, because that allows you, let me go up to here, or maybe I'll, okay, let me do this. That would allow you to reduce the error in the time evolution operator by, so this now is going to be order t cubed. So at the cost of twice the number of gates that I have to do for the first order, I gain 1 more power of t in the error. So if my t is a small, this is going to be a smaller. Okay? And there's also an exact relation for what the error is here, based on the double commutators of the terms and all possibilities. That's in the notes. I'm not going to write it down, but it's known. Yes?
Should I think of this as just applying the Baker-Campbell-Hausdorff formula?
Exactly. That's exactly that. OK, and then finally, what are the simulation strategies? And this is the part that you probably won't see in many papers written like as systematic as I'm going to say it here. It's kind of my collection of the kind of the steps that you have to like, or considerations that you have to do a simulation with product formulas. And I have given a reference when we talk in more details about what these strategies should be, okay? For simulating, strategies for simulating e to the minus IHT with product formulas. Okay, so we have to answer a few questions as we develop these algorithms. Question number 1, what is the best decomposition of H in terms of these terms? Okay, so in principle, we could have many terms in the Hamiltonian. How do we know how we sort of collect different terms together to be able to do sort of this expansion? So a few considerations here. Well, first of all, you have to know how to simulate as a whole each of these HIs. So if you have a collection of terms and you can't exponentiate all together and write it in terms of a set of gates, then you have to decompose farther. until the point that you know how to simulate that smaller piece. And you may say, well, why won't I just decompose all the way so that I know how to do it? Well, if you have more terms, then you're going to have more trotter error. So you don't want to do that. It's better to keep the terms together, not break them apart, so that we have less trotter error. It would also help to keep some of the symmetries, because as you break these terms apart, you may lose some of the symmetries, including gauge symmetry. So you don't want to do that. It's best to find the most effective collection of terms and then figure out how to simulate them. Okay? Question number 2. How to simulate each e to the minus ihit. Once you figure out what that decomposition should be, you should also figure out how to decompose each of those terms separately. And this is the most non-trivial step of every circuit construction, how to actually decompose this. And then I talk about this strategy in the notes and also in the reference that they've given. Sometimes it's a good idea to diagonalize this in your computational basis. If this would have been an electric Hamiltonian in the electric basis, this is already diagonal. If it would have been the hopping term in the Schwinger model, then it's not diagonal. So a good strategy is to first diagonalize that operator in order for find some unitary operator. Let's write it like this. And then turn that operator to e to the minus I some dit u dagger. And then as long as we know how what these unitaries are that would diagonalize each of these terms, and we have a quantum circuit that is efficient for these guys, as well as we know how to implement this diagonal operator, then we're done. And if this is already diagonal, you don't have to do this step. So again, you may say, how do we do this? It turned out that for most of the gauge theories that we're interested in, there is a very simple process of doing this, which is called the singular value decomposition algorithm. And that's one way to diagonalize these terms. And as long as those singular value matrices are simple to implement, which turned out to be for our gauge theories, then we can actually do this strategy. Again, more examples probably in the notes. Question number 4, or 3. So let me go to this slide. Which computational resources to optimize? Okay, so I'm coming up with a circuit, but there are multiple ways to circuitize an operator, it turned out. Which one do I pick? And that means that I have to decide what am I optimizing in terms of computational resources. So here is how it goes. If you're in near-term era of quantum computing, which is right now, then turned out that you need to use less Anshila qubits and less C0 or any entangling 2-qubit entangling qubits. Why is that? Well, we don't have very large machines, so we better save those qubits for the actual qubits that describe the physical system, as opposed to a bunch of Anshila qubits to do our algorithm. So if you have an alternative for the algorithm, we should pick the one that doesn't rely too much on Anshilas, like the Jordan-Wigner transformation. On the other hand, single qubit gates are pretty easy at the moment because we're not doing fault-tolerant decomposition of these gates. We are happy with certain accuracies, and people can implement these gates pretty fast. But on the other hand, the entangling gates are the slow gates at the moment. And because of their slowness, they incur more decoherence. So the less number of these entangling operations we can put in our circuits, the better in the near term. On the other hand, in the far term, when we have fault-tolerant, error-corrected quantum computers, then our strategies would be a bit different. Then we have probably access to thousands, hopefully millions of qubits. So we won't worry about enchiladas, okay? So cube, fine. But we have to limit less T gates or any non-Clifford gates. Because it turned out that in the fault-tolerant era, you have to implement every gate in a fault-tolerant way. I'm not going to tell you how to do that. Not within the scope of this lecture. But it turned out that, as I said, any quantum operations need a set of T gates. And in order to fault tolerant to implement those operations, then you decompose them in terms of a finite number of non-Clifford or T gates. And those are actually pretty expensive to implement fault tolerantly. Okay, these non-Clifford gates, in order to make them fault tolerant, they're very expensive. Yes? Depends. So if we're talking about there are different architectures. If we're talking about fully digital quantum computers, we are reaching of the order of hundreds. Like IBM gives you access to 120-something qubits at the moment, even on the semi-public side. So we're talking about orders of hundreds, tens to hundreds, but they are not error-corrected. And usually sort of a rule of thumb is that you need 10 qubits or order of 10 qubits to encode fault tolerantly just a single qubits. So you need 10 physical qubits to make one logical qubit. So always you have to have that in mind, that in the far term era of quantum computing, we really need a lot of qubits. But we also need to do the gates fault tolerantly as well. Okay? And then finally, question 4, given all these considerations, which formulation or bases states should we pick for our Hamiltonians? And that's why I spent a bit of time yesterday and the day before to talk about these formulations. Because in the end of the day, depending on what kind of physics you're interested in, what parameter ranges you're interested in, you have to understand how to best describe the continuum limit of your theory and certain other observables, and what would be the best basis to work with, given that you have all these considerations. Because you may go to a basis, and the Hamiltonian looks more complicated, even though you're more efficiently encoded because you have solved a bunch of constraints and so on, but you made it more non-local, more complicated, then you wouldn't know how to do this efficiently, maybe, or at least the circuits would look complicated. So there's always a balance between algorithmic side of things and the theoretical side of things. You want to recover the physics you're interested in as fast as possible with the least number of resources, but you also don't want to miss out on some of the simplifications that you can gain if you didn't do those assumptions. Okay? So with that all said, I'm going to give you an example now. Any questions? Yes?
So the only problem with the coherence is this kind of gates, like the entanglement gates, or we have another coherence?
Well, single qubit gates also have decoherence. Some of the qubits also have decoherence. Some others do better on that front. So the decoherence comes from various different parts of your circuit, not just the 2 qubit gates, but at the moment, the dominant decoherence comes from these slower 2 qubit gates. Okay. All right, so I have almost 15 minutes. I'm going to ask you to not ask questions for the next 15 minutes so I can cover what I want to say. And I'm going to stay here after 12, and then you can ask any questions that you want. All right? Okay. So because before not giving that example, it really doesn't do the justice to what we did, because we set up all these frameworks to be able to now implement some time evolution operator within this framework. Okay, so 15, yes. I wish it was 50, but it's not. All right. Okay, so let's talk about simulating Schwinger model, which is the one-dimensional QED that we talked about yesterday. And then I'm going to do it in, but at least in the first formulation, and maybe not in the second, but it's in the notes. So let's do it in purely fermionic formulation when we had this Hamiltonian, sum over x, psi, dagger x, u, and then we didn't have u anymore, so we had the psi of x plus 1 plus Hermitian conjugate plus sum over x. And then we had this fermionic operator, which was epsilon naught. Let's set this equal to 0 plus sum over y from 0 to x. And this is just one dimension, so I don't need this. And then we had the psi dagger x, psi of x, plus 1 minus, and I think this was minus 1 to the x, over 2. This whole thing is squared. And then we had the mass term, right? And then we have plus mu sum over x, minus 1 to the x, psi dagger x, psi x. OK. So we have these. So we have to first encode the fermions. And I'm going to use the Jordan-Wigner. And if you do the Jordan-Wigner, you suddenly realize that you have to replace this with a sigma plus, and this one with a sigma minus, with a bunch of sigma z's before them. But because this is a nearest neighbor interaction, all these, and this is one dimension, all these sigma z's are going to cancel each other out, except for the one that is sitting at site x, because that's like the one left over from this guy. But that one is trivial, because if you have sigma plus and sigma minus, already tells you that you either have 0 and up or down. Otherwise, the other possibility is just 0. So the sigma z that is acting on this is trivial. It gives you just positive or negative. That detail is in the notes. So that means that really this guy is going to only end up becoming sigma minus at x, sigma plus at x plus 1, which is really nice. This is the nearest neighbor, and this is sigma minus, sigma plus. And in fact, if I add this with the Hermitian conjugate, this is going to be just sigma x at x, sigma x at x plus 1, plus sigma y at x, sigma y at x plus 1. OK? So this is that term. What about this term? Well, this is going to be proportional to just sigma z. Because it's local, all those sigma z chains would cancel. What's your left is a sigma plus sigma minus, which is proportional to just a sigma z at position x. And similar with the mass term. OK? So our Hamiltonian is now essentially an hxx plus an hyy, where xx is this nearest neighbor term, yy is this nearest neighbor term. And then hzz plus some hz. Meaning that you only have operations that look like 2-qubit operations on nearest neighbor qubits, xx or yy. Or you can have zz operations, because this is z at x, but then it could also be at some other x plus d. And this is a squared. So that's why you get sigma z operations with certain coefficients. And they could be long range too. And that's that hzz. And then finally, you have single qubit operations. You get a bunch from this. Once you like multiply them out, and you get the mass term from this. OK? So now how do we implement this? OK, so now we want to implement e to the minus I h of Schwinger model t. And I'm going to write this as e to the minus I h xx, e to the minus I h y, e to the, and this is t, e to the minus I h zzt, e to the minus I h zt. So in other words, by doing this, I already told you what my decomposition is. I'm going to do all my x gates first, and then do the YY ones, and then the ZZ ones, and the Z ones. And that's not the only way that I can do this. I could have kept XX and YY together when they're acting on 1 and 2, 3 and 4, 5 and 6. And then I could act with 2 and 3, 5 and 6, and so on in another set of gates, because those would be commuting. Okay? So you can keep the ones that are commuting with each other all together and implement them together, and then have another set of gates. So that would have been another choice, and in fact, that's a better choice, because that doesn't break the total charge conservation symmetry. But then I picked this one. It's kind of simpler to show the circuit for this, but that one is also circuit, and it's in the notes. Okay? So then how do we implement this? Yes.
So that,
If it's quick. Bless you.
the quartic term, I see x inside of the sum over y. Where does y appear anywhere?
Oh, yes, that's a good, yes. This is y. Sorry about that. This is y, this is y, this is y. It's not good to rush. Yes. Okay. All right. So I probably take another 2 minutes, and then I'll go to this slide. So, all right. So how do we implement this term in terms of a quantum circuit? What is this term? This term, let's go with the ZZ term. It's kind of simpler to talk about this first. E to the minus I, some sigma z that is acting on qubit, let's call it J and K, and then sigma z, some qubit K, T. How do we implement this? Okay, so this one is not just a single Z rotation, it's a double Z rotation. Okay, so the way to do this in terms of the universal set of gates is the following. And then these are your C0 gates. This is equivalent to this. And this is simply e to the minus I. If this is your qubit J and this is your qubit K, this is just sigma J times T. So the trick that I did was to just turn this into a single qubit Z rotation at the cost of introducing 2 C0 gates. You may say why it works. Well, just convince yourself that if you have 0 and 0 here, then no phase change should occur, because this is positive times positive. Okay? And then if that's the case, then this is 0, this doesn't change. You get just the 0, which is like no phase out of this. The only cases that you have to worry is that when these are like up, down, and down, up, 0, 1, and 1, 0. So if this is 1, that would change the 0 to 1. And therefore, so let's work at 1. So if this is 1 and this is 0, you have to have like a negative sign coming out of this. So what happens is that you have 1, and this turns, because of this, would turn into 1. So you get your negative sign out of this, and then you kind of revert them back so that you have your original thing. So all the signs would work out. You don't need to implement both of them together. You can just couple them first with these C-nots and just implement one of these Z rotations. This is a very well-defined, well-known trick, okay? So what that means is that these guys can be done in a similar way. And in fact, if you want to just do the sigma Z rotations, then you just do single qubit rotation in that basis to go from X to Y to Z basis. But each of them is going to be at, between each pair, is going to have 2 C0 gates and then 1 RZ gate. And obviously, this is simple because this is just a single RZ gate on each of the qubits, right? So you have things like this on each of the qubits. Okay? And all right, so I want to switch to the slides, but one last thing is that the total cost of this simulation you can already see that for each trotter step, you have n number of qubits, and then in order to do those operations, you have nearest neighbor interactions, and you have also all-to-all interactions. So if it was just nearest neighbor interactions, you only need n number of entangling gates, or 2 times n, but I'm not keeping track of that. But because of the ZZ interactions, you have to connect them for all pairs. So you get order n squared C0 gates for each trotter steps. Okay? On the other hand, if I had gone to that purely bosonic formulation that is in the notes, and I didn't get time to talk about this, then you can actually see that you can have better scaling, but on the other hand, you have more number of qubits, but you're not really sort of winning. And there is a comparison in the notes about which one eventually would win over the other ones, but I'm gonna go through that. Another thing to notice is that I didn't tell you how many trotter steps. How do you know that? Okay, so in order to know that, you have to tell me what accuracy you want on your time evolution operator in the end for a given simulation time, total time t. Once you give me that, then I go and calculate the trotter error associated with that evaluation. And then given the parameters of the Hamiltonian, the total time t, and the counting that we did for the number of gates, I can tell you total simulation cost. So circuitizing is only one step. In order to give you the full resource requirements of simulating a theory like this, I have to also determine what accuracy I'm after. I have to calculate analytically in other ways the error associated with my algorithm, which is in this case the trotter error, and then turn all of that into a total simulation cost. Okay? So let me switch to the slides and show you a few nice examples. All right. Okay. So I have some notes about outlining the differences between abelian and non-abelian theories. For those of you that were here to talk about non-abelian theories yesterday, these are a few things that you can look at. And obviously, I didn't have time to talk about a lot of things because it was just 3 lectures. I didn't tell you about other formulations of gauge theories in different bases. We didn't talk a lot about non-abelian theories. I didn't tell you how to prepare states, how to do measurements of a scattering amplitude and things like that. I have a bonus lecture now that is I'm going to upload for you. You can look over that to get some idea about these other steps of the simulation. We didn't talk about error mitigation and error correction at all in this context. That's also a very hot topic. And I didn't talk about quantum hardware architectures and how we can simulate gauge theories in a way that is more aware of the hardware requirements. That's also a very hot topic, and kind of co-design the hardware for gauge theory simulations. But what I'm going to do in 2 minutes is to just quickly show you what people have done so far with these hardwares that are out there. Okay, so there's been a lot of theory work that is out there. These are examples of different formulations of Hamiltonian gauge theories. Most of them start with Kogan and Susskind that I talked to you about, but they get more complicated. So there is a zoo of choices at the moment that people are developing. Here is an example of simulating the Schwinger model. The seminal work in Europe was about in 2016 when they did a trapped ion quantum computing simulation of the vacuum of the Schwinger model in real time and saw the pair creation and so on in a very small system. That's exactly the model that I put on the board, and that's exactly the circuit that they implemented. So it was very relevant, and it was, in fact, forefront physics in 2016, okay? But there's been more simulations of the Schwinger model. There's been now simulations of a small non-abelian gauge theories, not only in 1 dimension, but also in 2 dimensions, in higher dimensions, hopefully. There are simulations of hadron spectrum in the same models. So these are a few examples that you can look at. There are now simulations of hadron state preparation for scattering and wave packet preparation. This is an example in 112 qubits with the IBM. which came out a few months ago from the Seattle group. So you can see the state of the art. That's over there. This is another example with trapped ion systems to simulate the hadronic wave packets in a gauge theory. There are now prototype simulations of beta decay in one-dimensional QCD. So that's another example over here. You can look at things like Parton shower, and you can ask Ben about this. This is one of his work with his colleagues. How can you come up with the quantum algorithms for Parton shower in LHC? How can you write algorithms for Parton distribution functions of things like proton, at least in simple models? There are ideas for this. We can look at the phase diagram of matter at finite density, finite temperature, and there are algorithms to do that. We can look at things like shear viscosity, which would be very hard using our current Monte Carlo techniques. But again, one of those examples where quantum computing can help. You can look at things like non-equilibrium dynamics, thermalization, topological order, and dynamical phase transitions in gauge theories. Again, all small systems and simpler models, but gives you an idea of what kind of quantities are accessible eventually. And I have this slide to say that there's also a lot going on in terms of developing algorithms or co-developing algorithms for particular hardwares. For example, if you have qubits, multidimensional Hilbert spaces, bosons, fermions, can you take advantage of those and simulate these bosons and fermions more directly as opposed to encode them into a bunch of qubits? There are lots that are going on in that space as well. So you can check out some of these recent developments. And really, finally, we've gone a long way, but there's a lot to do because we haven't reached QCD yet. Well, first of all, we don't have the hardware. We really need tens of thousands of qubits and millions, if not more, number of gates. But we also need to develop a little bit more in terms of